Hey everybody, this is Larry. This is me teaching the concepts of prefix sum. So prefix sum is just a word that comes up from time to time. What does that mean, and how do you use it to solve problems? And then I'm going to go over a hard problem that came up recently in a contest to kind of use as an example to go for. So at the way basic thing is that prefix sum is just let's say you have an array of numbers. I'm just randomly generating them, and now let's say you have a prefix sum. So you could write something like, I'm using very big font. Hopefully that's okay. And nums is equal to this thing, say, right? And you could do something like for x, for x and nums. Let's start with 0 as a prefix because that just contains 0 elements. But I'll go over what this means in a second, right? X plus prefix sums, the last element of prefix sum, return prefix sums. So then now we can just print nums and prefix sums, right? Oops. We'll print one real quick. Did I mistype it? Oh, whoops. Right, so then now we have these two arrays. Right, so that's okay. So that's what prefix sum is conceptually, and obviously, it's very easy to write. I wrote it live, even though with a typo, in about 10 seconds or so. But so what does that mean, right? What is prefix sum? How is it used? That is the more interesting question. And the idea is that, okay, so basically you have this segment that gives you the answer, and 0, again, represents the empty segment, right? So let's say, well, I mean, the way basic, the prefix sum of, let's say you're trying to get the sum of the first k numbers. Well, this is pretty straightforward. This is the first, so now, the first, let's say you're trying to get the first number, then 0 is going to be your first number, the sum of the first number. Element 1 is going to be the sum of the first one number, sum of the first two number, the sum of the first three number, and so forth, right? And then you kind of figure that out. So that's the, very basic prefix sum, literally, just the sum of the prefix of the index that you're looking up. And it may come in handy. You could kind of think of it as, I wouldn't say it's quite that, but you could kind of think of it like memorization, where, okay, you remember it so that you don't have to calculate it over and over again with a lot of for loops or something like that, right? So that you could do this in all one time. And then another thing to notice is that this is very similar to dynamic programming, and that's, maybe a coincidence, maybe not, depending on how you want to think about it, but that's kind of one thing, right? So basically, let's just say this is k, or let's just say this is p. P of I is equal to the sum of the first I numbers in array A, where this is A, right? So basically, you have that. Maybe I should just do. Right. Okay. So that's the very basic, query. You should be able to look it up. And how do you use this? Well, when you solve problems, when you see yourself thinking, okay, I need to figure out the sum of the first k numbers. Well, this is what you would do. I mean, for problem solving, as I always say, you always try to find the right question to ask, and then have data structures to fit those questions later. So the question here generated to be answered is, what is the sum of the first I numbers, right? So that one is obvious. That is literally what this one does. And then another question that you can answer actually is, what is the sum of the numbers between index I and j, right? So let's for a second, let's just say, yeah. So basically, this is a little bit trickier, but still should be solvable. Let me know if you're able to go ahead, pause for a second, see if you can figure it out on your own if you haven't already. But the idea is that, okay, so basically you have, so basically you could rewrite this another way, where p sub, let's just say you have p sub I, which is what we have, enters a function from f of I to 0, which is now instead of saying that this is from first I numbers, it is the sum of the first, of the numbers between index 0 and I. I think I minus 1 actually, but yeah. And therefore you could do it again for j, which is sum of the numbers between index of 0 and j minus 1. So maybe you have to do like plus 1 or something like that, but no. But yeah, right? Let's just actually to simplify this, let's add 1 here. 0 and j, right? So then now the question is, what is the sum between index I and j? Well, if you write it out, p sub I is equal to a sub 0 plus a sub 1 plus a sub 2 plus dot 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 plus a sub I minus 1, right? And p sub j is equal to a sub 0 plus dot dot dot. I'm going to dot 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 this. And of course, we assume that j is greater than I, because otherwise you could swap them, right? That's not a big deal. Plus a sub I plus dot 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 plus a sub j minus 1, right? And then now you could, and as we said, p sub I is equal to f sub I plus 1 0, j plus 1 0, right? And then now to get this function that we're asking, which is ji, I think maybe it should have been ij, I did it the other way, but is equal to, what does this mean, right? That means that to get this function, all we have to do is just well, how do we get from I to j, right? Maybe another way to think about it is, let's say we want this function, right? Maybe a little bit of spoiler alert. Maybe I'm going backwards a little bit. So let's say now we want to find this function. And now this function is, if you look at it again, is just this function minus this function, right? Because a sub 0 cancels out, a sub 1 cancels out, a sub 2 cancels out, dot dot dot, right? So now this is just equal to f sub j plus 1 I plus 1, right? Well, I had a weird off by 1 here, but let's just say maybe I'm a little bit off by 1, but that's the general idea. So basically that's the prefix sum, right? Because yeah, so that's the prefix sum, and that's how you kind of figure out prefix sum by using these things. And that's kind of the step 1 of the prefix sum. And it's it's very specific, it's hyper specific to sums, but you can think about this generalizing to other ways, right? So for example, let's say our function right now is adding, right? Let's say we use prefix pi, or whatever you want to call it, like the prefix of the product, right? Prefix product, maybe that's a better word. Whoops, not prefix. Yeah, let's say we replace it with this, right? Well, I didn't finish replacing yet. And we want to get, this prefix or this suffix. Well, then in this case, this is just equal to this thing, right? And how do you get this answer? Because that's what we're looking for. I mean, it's equal to this thing, but how do you calculate this, right? Well, this is just calculated by taking, oh, I think I missed a step before, this thing divided by this thing, right? So before, in the addition version, I didn't write it out. It is just this minus this in the additional addition version. So this is from before. Because as we showed before, it cancels out, right? And similarly, if you have something like this, the way to cancel out the prefix is by dividing, right? Because then now you have this as a product, you have this as a product, this cancels. If you write this over, if you just write something like this, like arithmetically, something like this, like a long line, like it's in grade school, you have this. Well, what happens? Well, this cancels out because this is just 1. A sub 0 over a sub 0 is just 1, right? This cancels out, this cancels out, and then dot dot dot, and then everything cancels out except for this, right? So that's how we come with up with this formula of, and that's how you would do the inverse prefix sum, right? So, but another way to write this, of course, and now we have two functions that we kind of did. They're based on different premises, so bear with me for a second. But now you have these two things, right? But maybe another way to write it is that right now we have some contribution, right? Like this is the entire thing that we have. We store numbers up to here, or we want to keep track of, let's just say we want to query these last X elements or something like that. Well, it's just going to be the way to get this is just you go to this, do some inverse of this, right? So that it cancels out. That's the kind of the answer, if that makes sense. Okay. Right. So that basically we want. So this is equal to some function f of, as we said, let's just say I0, or I guess this is technically j in the same notation. So this is some j sub 0. This is equal to f sub j I, which is roughly speaking f sub j 0, some f of prime of I sub 0, right? And this is just the inverse function. As you kind of maybe intuitively gotten, we subtract this because subtraction allows you to cancel out the addition. So this is the inverse function, the identity function for that space. And for division, or for multiplication, division gets you back to 1, so it allows you to cancel out, right? So with all, yeah, one thing I want to add is also that now that we have this formulation, we can actually store different things in an array, right? I mean, right now, for example, we have this stored, but let's say that we know that we're always gonna query the suffix, right? So that means that we have a running counter. We know what the last element is, and then you want to go backwards and just calculate the inverse of that, right? So we can definitely do that. Let's just say n is equal to, let's start at 50, and then this should be, 0, -8, -9, -14, basically negative of these numbers, right? And what am I doing here? Well, now what I'm doing here is that these are reference points from 50, the last digit, right? So that means that if we want to get the suffix sum, if you want to call it that, then it is just the last number, which is the total sum. This is based on that the sum minus the n of index is equal to, oh sorry, this is plus, right? where this is equal to the suffix of the array. So in this case, for example, to get 29, we would get, to get the sum of these three elements, we would take the negative 29 that's here and then add it to 50. So this is just the inverse of it, and you could kind of do the same thing for the multiplication as well. So this is going to come in handy as we work toward the more difficult problem of what we're doing with fancy sequence. Fancy sequence is a recent hard problem on the leetcode contest. And basically what we're doing here is that instead of, let's say we have prefix sum, we wrote it like this, but another way to write prefix sum or suffix sum maybe, let's just say suffix would be, let's just get the, let's just say this is the current count is equal to 0 for x in nums. Actually, let's just do this, right? Prefix sums, append, prefix sums, the last number minus x, right? The inverse, of what we did. But maybe another way to write it also is just total is equal to 0, total do x, and total plus no, total minus, no, in this case, and then now we can return the prefix sums where we return this pair where you can find the suffix of the number by looking at the total and then just subtracting from the index, right? Again, this is just literally here where in this case, let's draw more dots, for example. Like this works for any general case, but let's say that now you have only the suffix to worry about. Then now we keep and this is just the running count. And then this is what we look up in the lookup table. And this is then just the some operation on the running count and the lookup table, right? And this allows you, so the way that we do it allows us to kind of keep the same f instead of using the inverse f, because in this table we would actually store the f sub sharp, right? So that basically, like, you kind of think about just ways of canceling them out. And this comes in handy, again, when we talk about fancy sequence. One of the problems that we have on LeetCode contest on question 4. And basically the idea is that in this case, you could think of f sub I sub 0 is equal to, and also another way to write these are that, this is I minus 1 sub 0 times some m plus some c, right? And keeping in mind that we can also write this in as g of f sub this, where g of x is equal to this inverse prefix number, right, of x sub 0 of which is just equal to some inverse function of based on a sub I x, right? So basically now that we have these functions, that's basically all we need. In this case, we kind of, well, we have to also take care of mod. So basically what we have here, that's ignoring the mod for a second, it's that for example, in a normal case, we could store this as this plus c, right? But because we care only about the prefix, we actually want to store the inverse version, which is, we do some I minus 1, 0, and then we minus c divided by m, right? So basically this is the inverse of this function, because if you could try it at home. This function, g of x is equal to a sub x times m plus c. G prime of x is equal to x minus c divided by m. And you could kind of try it at home. That the reason why this works is because they cancel out, right? And once you have those two ideas together, then this becomes straightforward. You could think of you can think of it that way, and now it just becomes a prefix sum problem, even though this is very fancy in math. But basically now you have some number, and then you want to keep track of this constant. Like we said, we just keep track of the negative version of that number, and we calculate it by some offset as well, as these things move on. And modular inverse. So the reason why we have modular inverse is because of this mod thing, because otherwise it gets too big. So I would do some Google search on modular inverse, but basically the idea is that instead of you can think about ax is equal to b mod say. So now to divide a on both sides, to get x, you get ax. In theory, what you want is something like this, but what actually happens is that you need something called the modular inverse, so that b times a sharp or a prime under mod is the same, and the idea is that this a prime or a times a prime is equal to 1. Mod it, right? So that in this, as long as this holds, then this will be true. And a couple of ways to kind of find a modular inverse. Not all numbers will have modular inverse. If mod is prime, then they're relatively prime, then the modular inverse. You can read this up on Wikipedia, and that's basically how I solved this problem very quickly afterwards. Basically, I keep track, and you could look at the constant and the multiplier as kind of prefix sums as we kind of go on, because when we have a constant, okay, well, we just increment it. We also make sure that we mod it. When we multiply by a number, we have to multiply by the constant and the number. You can kind of think of it this way, right? Like if you have a number a and you add x, then it's just equal to a plus x, right? I mean, this is straightforward. If this is, let's say you have ma plus x, and we want to multiply this number, then, well, you get, I guess you want to call it this, it's equal to plus increment, right? Let's say you have a function that's already this, I'm terrible, and you want to times it by m, that's just equal to mia plus mx, right? Okay, variable name aside, that's basically where these two function comes from. And then, so this gives us basically this values that we store, because we already divided by and we subtracted and then we divided it. That's what inverse constant and inverse multiplier means. That means that basically there are two ways to solve the prefix sum, right? Think about this prefix sum. one way would be that, you know, you have this long length of things, and then, you know, you have this number. So then right now, in order to get this middle chunk, the suffix, we basically take the value that's here that takes account all the numbers, like it already, when we appended in here, this number is already divided out, right? Because what I mean by that is that this is the inverse function, and this inverse function times, so, you know, this is g sub x, right? And what happens is that if we do g sub x like that, then it should equal to the value that we have, right? Or x, because I guess x is not an index. And that's basically why we did it this way. And basically, once we append that, and then going forward, we know that, you know, every time we keep track, we move that constant forward. It is a very tricky problem, but if you understand the math, then it's not so bad. And you could kind of try it with yourself, with kind of just keeping track of the multipliers and then divide it, just to kind of show to yourself. Though this overflows very quickly, but that would be the visualization that I would take. And yeah, that's all I have for this problem and prefix sum. Let me know what you think. Hit the like button, hit the subscribe button, join me on Discord, and I will see y'all soon. Bye bye.